Morning, everyone. So my name is Karl, like Stefan said, and I finished computer engineering at Tux last year. So I'm going to be talking about the impact of software on solar. So there's a bit of a backstory as to why I chose this topic. In January, one of my friends or family friends installed a solar system because they work from home, and load shedding was wreaking havoc on their work. So I was visiting them for a cup of coffee, and I thought, wow, solar system's really cool. Let's have a look. So when I had a look at their solar system, I saw that the panels had been laid flat on a corrugated iron roof, and something in my brain just didn't quite click. So I began to question. Solar panels are usually placed at an angle, aren't they? Surely they get hot from the sunlight reflecting off the roof. Wouldn't it maybe be more efficient if they track the sun? So, being an engineer, I decided the easiest thing to do would be to download some simulation software and check if their solar panels were actually placed properly. So the majority of my talk will be an interactive demo, but I'm going to first provide some background information on the symbols that are used for electricity, so that the simulation software makes a bit more sense. And then I'll also very briefly cover the basic components of a solar system. So I think the easiest way to conceptualize electricity is by using water as an analogy. The three basic components are voltage, current, and resistance. So voltage is a potential difference, so think pressure in a pipe. Current is a flow of charged particles, so think the size of a hose. And resistance is a measure of the opposition to current flow, so think any blockages in the pipe. If we then think of energy as the amount of water collected from the pipe over time, so water in a bucket, power is the rate of transfer energy, so water flow rate. The unit for power is the watt, and the unit for energy is then kilowatt hours or watt hours, essentially a unit of energy times a unit of time. The final important concept is AC or alternating current versus DC or direct current. So AC currents alternate between or oscillate between positive and negative. So think water flowing backwards and forwards in a pipe, whereas DC currents flow in only one direction. So again, think water flowing only in one direction. With that, we can move on to some solar basics. So an important technical aspect to note is that solar panels produce DC, while mains voltage, or what you use for almost anything, is AC. A solar panel's voltage output also fluctuates throughout the day. So an MPPT charge controller can be used to control the solar panel output to make sure it's more constant and can actually charge a 12-volt battery at typically 13.8 volts. MPPT stands for maximum power point tracking, and it's a bit beyond what I'm going to cover here, but essentially it helps maximize solar panel output. The DC from the battery is then converted to AC via an inverter, so that's shown there. Inverters make use of high-speed switching circuitry to mimic a sinusoidal output before passing it through filters for smoothing. So I have a graph here to show how solar panel efficiency changes based on how many axes the solar panel tracks. It's pretty intuitive. Obviously, if the solar panel directly faces the sun throughout the day, it's going to produce more electricity than if it doesn't. It's just important to note that it can track along two major axes. So you can see it can rotate, and then it can also move up and down. And then the blue graph is for flat solar panels. So if it was at a constant inclination, then red is if it tracked along one axis. So that would be the tilt axis. And then green would be if it swivels and tilts. So with that, I'm going to move on to the demo. Cool. So solar software has evolved over time, like any other software. Originally, it was quite basic. There's tons of websites like this exist. Essentially, what you do is you give it your location, and it pulls weather data from various databases and tells you sort of what you can expect your solar panels to produce on average. So here I've chosen the BBD rooftop, and it's saying that on average, every year I should expect around 2,100 kilowatt hours per meter squared of solar panel area that I have on the roof. So cool, it gives me some sort of idea, right? I don't know how temperature is going to affect it. I don't know how shading is going to affect it. All I know is that I can sort of expect that under perfect conditions, and then I can see how much I'm going to produce per month in general. So cool, that's sort of iteration one. It's better than nothing. Next, it sort of evolved to include Google Maps, actual topological data. So in this case, again, BBD rooftop. But now this software lets me pick where exactly I'm going to place the panels. So what I've done here is select the BBD rooftop. And I've said, cool, I'm going to place solar panels in that area. So now what it's done is it's gone and said, cool, for that area, you can have a system size of 41.5 kilowatts. And then again, I can look at the results. The difference here is that now it's actually using the size of the solar panel array that I can put on the roof. So a bit more accurate, still doesn't quite show everything you'd ideally want. So then we get into industrial scale software, right? So this is significantly more accurate. What you can do here is load weather models. So they've got a couple different sources. Okay, so I've loaded my weather data from Meteornorm. You can go with NASA, SolarCast, there's a whole bunch. You can even average between different providers. And then what's cool is it actually shows you the sun parts. So now imagine us being at the center of the rectagonal diagram, and then that's how the sun moves over us from east to west. You can see there's actually a bit of curvature to it, right? Doesn't directly go overhead. So now I have an idea of how the sun moves. I know where I am, and I know what the temperature looks like. Cool. What I can do is I can actually tell the software how I want my panels to behave. So like I say in the demo, obviously if your solar panels track, they'll be more efficient. So what I've done here is I've made a track along one axis, and then I've actually gone and created a little CAD model of BBD. So here's the rooftop. There's our little solar panel array. And then I've just got a rough mock-up of the buildings around us. So these two blocks here are the apartment buildings, and then this is the Virgin Active. Very approximate, but you can get as complex as you want. It supports SolidWorks, Fusion 360. It's pretty common feature now. Then based on this, we can actually see how shading affects the panel output throughout the day and throughout times of the year. So here's that same graph from earlier, except now you can see that the certain regions are shaded. So the areas enclosed by those black lines show where you're losing solar panel energy due to shading from surrounding buildings. It's not something you'd generally be able to work out without physically going and standing on the roof in the location you want to put solar panels and checking how shading affects it throughout the day, right? So this is saving us a lot of time already. Then I can define my system. So you've got a maximum area based on your CAD model. And then I've just chosen 550 watt solar panels here because they're readily available, can find them easily online, and just a 9 kilowatt inverter. But now, not everybody is an electrical engineer. So it gives you information about how you should be setting this up for maximum efficiency. So here it's telling me I should put 9 solar panels in a row, and I should have 8 sets of that. And then it says I will need 4 inverters, and my total output will be around 40 kilowatts. This also considers data sheets for the different components, so that it can consider the exact solar panels that you're using. You have a very accurate picture of what's actually going to happen. And then finally, there's an economic evaluation aspect to most industrial scale softwares now. So what I've done here is I've just grabbed the prices online for those solar panel modules that I chose, the inverters, some installation costs, insurance, some running costs. And then what I've actually done is I've said, we're going to get the electricity or the original price of everything from a loan at 15% per annum interest, and it's going to be a 10-year loan term. And then when you run the simulation, it'll consider the actual energy produced by the panels, including electrical losses, shading losses, everything, and then do a analysis on the payback period and how profitable your venture will be. So here it says, based on the BBD rooftop with the panels I've given and the prices, it'll be paid back over 8.8 years. And what's kind of crazy about that is if you look at the results, our solar panels are actually only reaching a peak efficiency of 28% on the BBD roof. So now I didn't place the buildings 100% accurately in the software, but according to this, we're losing around 70% of the possible electricity generation due to shading from adjacent buildings. So maybe in this case, it wouldn't be worth putting solar panels on the roof because of the shading. And you wouldn't know that before software like this came around. What's also interesting is you can see here, based on this graph on the left here, so that's the amount of energy versus time through the months of the year. So that's how much you should be able to produce from solar based on the time of year. You can see it dips in June and July. But actually, based on this performance ratio graph on the right here, at BBD, the production would be the highest in June and July due to how the shading changes throughout the different times of the year. So these sorts of insights wouldn't be possible before software like this, and that's why software is revolutionizing solar.